No, there.
Okay, just short and sweet, do they have to use the liposomes for that as well, or is that like a, I know we can't go there, I know, but
No, they don't have to.
they don't have to.
And what you're referring to is like Adrian Moss. Yeah, that's the red devil that stings like crazy. Taxol is paclitaxel, and it's not, it doesn't have its side effect. So you can just infuse it straight into a vein. Very good question. But to my knowledge, I've not had chemo, but to my knowledge, paclitaxel is not like Adrian Moss. Very good question. Okay, so this is the home from which all microtubules grow. Each microtubule, which is made up of 13 protofilaments, originates from this thing called the gamma tubulin ring complex. You have to know this. We're going to let the other two go. We're going to keep this one. So the gamma tubulin ring complex is nothing more than like a pot in which you plant some seeds, and the seeds we're going to be planting are the protofilaments growing out. But this pot has a very definite makeup. That makeup is composed of proteins that are shown in blue. You don't need to know the names of them. But a weird tubulin. Remember, these were alpha, beta, alpha, beta, alpha, beta tubulin. There is a gamma tubulin that is part of that group of proteins that form the nucleation center of the microtubule. So gamma tubulin ring complex, often abbreviated like this. Try and make it big because I know the lights are on. Gamma TURC. That is gamma tubulin ring complex. Okay. See that circle, that ochre colored circle? That is a gamma tubulin ring complex. This big green thing is your centrosome. The centrosome is the home, if you will, of all microtubules. So all of these gamma tubulin ring complexes here will be the nucleation site for microtubules to come growing out of them. Another name, loosely applied, for the centrosome is the microtubule organizing center, or MTOC. And you have to know that. So the centrosome equals MTOC. In our book, it's a minor difference from MTOC. MT is just always going to be microtubule, and then organizing center. And it's in the centrosome that you have all of the gamma tubulin ring complexes embedded, and then the microtubules will be growing out from that.
How many MTOs do we have in a cell?
Just one. Which, if you think it through very, very deeply, you get all confused because you've got a plus end and a minus end. Because the minus end is supposed to be slower growing. It actually can't grow because it's stuck. I don't know if that's what you were thinking. Yeah. I was trying to explain it. Does that make any sense? It's just a convention of how it's slower growing. Actually, you stuck the pot in the ground. I think some of these terms got named before we really had the great resolution. Being able to see inside the cell.
So the
Okay.
centrosome, it has the microtubule organizing center, which has.
It is.
It is.
It is.
I'm sorry, it
Here's
is.
the centrosome.
Yeah.
or here is the microtubule organizing center, that whole big green ball.
Okay. And in there, there's the gamma tubulin ring complex?
Exactly, these red things.
And then the microtubules, the alpha,
They
beta, those are
come
things that
out
come
of the
out.
gamma tubulin ring complex.
Okay,
Mhm.
yeah.
Okay. I know, is this going? Okay, this section deals with the microtubule associated proteins, and that is G as in goat, or good grief, on your outline. We're not gonna name them. I just wanna tell you that what these microtubule associated proteins, MAPs, are simply proteins that stick out from the microtubules. So you're going, oh, so what, why? Well, look at the spacing that you can get. If you have this particular microtubule associated protein, it has a long arm on it, it keeps the other guys that distance away. If you use a different microtubule associated protein that's only that long, the microtubules can group in more closely to one another. That is of significance, but we can't go into that, so. Don't worry about this. Just microtubules grow, they shrink, grow, shrink. That's all you have to know. Don't worry about this one either. If you want to just take a peek, see that GTP on beta? That's the one that gets cleaved. That's all you have to see there. There's one over here on alpha. He didn't even bother to draw it because nothing ever happens to it. It's just a dud. Remember, we're using these differently than what your legend will say in your book. Okay, growing, polymerizing, shrinking, depolymerizing. Beautiful EMs of that. Here's a microtubule. And this is the thing along which your microtubular motor protein walks, carrying cargo. That's like you just saw in the beautiful film. Every time this microtubular motor protein, green, dark green, goes, every step burns ATP. Got another use for ATP. So if you run, you're using a lot more ATP. I don't know if they can run or not. Okay, we're not gonna worry about this. I'll just tell you what it is. There are two different flavors of motor proteins. Some of them walk one way, some of them walk the other way. One is kinesin, one is dynein, and you don't have to know that. This is what happens with a flagellum. A flagellum is the singular for flagella. A flagellum on a sperm. So that is going to be similar to a cilium, which would be cilia, plural. It is because of the motion of microtubules there that you're able to have the sperm swim up the fallopian tube. My fingers don't do that justice, but you can imagine a power stroke recovery. My finger won't go back and forth, it will just go one way. But it's because of the microtubules in there that that's possible. The cilia are lining your bronchial tubes here. So when you have, like in this horrible weather we're having, we're all coughing up this crud, it's actually the cilia in there on your pseudostratified, ciliated columnar.
Yeah, columnar.
It's been too long ago, but those cells, those cilia are bringing it up so you can spit it out. I don't know what else to say. Okay, so that's important. We're going to look at the cross section. We're only going to do the flagellum or the cilium. They have the same structure. Let me warn you that there's a basal body in here. On farther down, we're not going to do that. We're only doing cross section of cilium or flagellum. Now say thank you.
Thank
You're
you.
welcome. Because students always get the two mixed up, so this way you can't get them mixed up. All right, here we go. That's a real EM of it. Here's a drawing. Use the drawing. The cartoon is much easier. All right, now let me help you get your orientation. You see that thing? It has 13 dark circles in it. That is a complete microtubule. 13 protofilaments. If you look out here on the edge, you have a complete microtubule, but right next to it is one that is incomplete. The incomplete only has 11 protofilaments. You're going to have to draw this. This is a cross section of either a cilium or a flagellum. And the reason that we are able to do that kind of a motion is that you have other proteins, the red and the blue, we're not going to worry about names, hooking these microtubules together such that you can get this ratcheting movement and cause that wiggle. Okay, here's what is referred to as the 9+2 pattern. That's just always what it's called. So in cross-section, a cilium or a flagellum has what is called a 9+2 arrangement. When you draw it, you be sure that you identify each circle. You don't have to go around 9 times and do it, but you have to identify. Otherwise, it's just a bunch of circles. Okay, here we go. In the middle, that's the +2. 2 individual complete microtubules, and those dark green should be 13. Protofilaments. Now you have 9 of these doublets going around here, where you have 1 complete and 1 incomplete microtubule. That's what you have to draw. And you have to be able to label it. It's beautiful. It's just beautiful. That is just such a perfect structure there. And if you didn't have that and didn't have these interconnecting proteins, you would never be able to get a sperm to swim up the fallopian tube. It just wouldn't happen. All right, these are the motor proteins going along. They're all headed that way.
Very quickly, is that what's wrong with people with cystic fibrosis then?
That is part of the problem. There's a her question is dealing with cystic fibrosis. And there is a problem with their chlorine transporter in their membrane. And it's messed up chlorine transport. It's really at the base of that. But it is also related in an indirect way to the microtubules. So these are all headed that way. Down here you picture the other ones headed the other way. Isn't this beautiful? This is my favorite EM in the whole world. Because that's actually a motor, a microtubule, and those are motor proteins. Isn't it beautiful? And these are headed that way. How did they get that? I mean, just perfect. Okay. Not gonna worry about it. We just can't. These little things in between here, the red things, are equivalent to what you saw here. In other words, they're hooking those microtubules together, otherwise you wouldn't have them to move. Now, don't look at this. You look at it, but don't get it mixed up with what you just did. This is the basal body in cross-section. We're not doing basal body. That's down lower. If this is the flagellum sitting here like this, what we were doing was a cross-section right up about where my wrist is. Down here where my elbow is would be the basal body. It has 9 sets of triplets. There's really nothing in the middle. That's a remnant of the preparation. So don't worry about that. That's a basal body again. 9 triplets. Each of the 9 is 1 complete and 2 incomplete, in case you're interested. Okay, we're going to go on to part 2.